A string on a guitar is the second lowest string, since E is the lowest. This one ideally plays an A at a frequency of 110 Hz, 2 octaves below the A from the previous problem. The length of the string is 0.648 meters and the tension is 100 newtons. Part A asks us to sketch the node pattern when the string vibrates in its fundamental mode. A string is fixed at both ends or closed at both ends, and therefore both ends of the string are nodes. This means that the fundamental pattern looks like this. Most often a guitar is played in the fundamental mode. Occasionally, however, during tuning, a guitar player might play a guitar in this mode, which is the next one, or even if they're particularly proficient in this mode. However, since we've been asked for the fundamental mode, this is the answer to the first problem. However, we're going to use these sketches to derive the relationship for the frequencies of a guitar string. In the first case, the length of the string is equal to a half wavelength. In the second case, the length of the string is 1 wavelength, which we'll write as 2/2 wavelength. In the third case, it's 3/2 wavelength, etc. What we note is that the length of the string is always equal to some number of half wavelengths, or we can specify those as lambda sub n. Since we hear frequency and we don't hear wavelength, we'll rewrite this using the velocity and frequency so that the velocity of the wave, which does not change as n increments, is in the numerator, frequency is in the denominator. This yields the formula for the set of frequencies on a closed musical instrument to be that f sub n is n over twice L times the velocity of the waves. In part B, we've been asked to find the mass per unit length, mu, of the string. We'll do that in the following manner. We note that since the guitar will typically play in its fundamental mode, the frequency we're talking about, F1 of 110 Hz, will be equal to 1 over twice the length times the velocity of the waves. The waves on a guitar are carried in a string, and we remember the formula for the velocity of waves carried in a string to be the square root of the tension of the string over the mass per unit length. Plugging in the fact that we know the length and we know the tension, we get the following result. 110 Hz is 1 over twice the length times the square root of the tension of 100 newtons divided by the mass per unit length mu. We can solve this for mu as follows. And plugging the numbers into this expression, we get 0.00492. This result will be in kilograms per meter, and just for convenience sake, we'll change the units to grams per meter, which will give us 4.92 grams per meter. Finally, in part C, you wish to play a C note, which is a frequency of 131 Hz on this string. How do you accomplish this without changing the tension or the mu of the string? Specify your answer as an exact numerical result. Well, what we know is that you change the note on the guitar by placing your finger on the neck of the guitar against one of the frets and thereby change the length of the string. You will still play the guitar in the fundamental mode. This means that the frequency will be F1, which is 1 over twice the length, times the velocity, and for waves on a string, the velocity of the wave will be the square root of the tension over the mass per unit length. A common error made by students in a problem that involves a guitar or a violin or any other string instrument is to change the mu when you change the length of the string. After all, mu is mass per unit length. However, even though you have changed the length of the vibrating string, you have also changed the amount of mass that is vibrating, leaving the mass per unit length, which is a characteristic of the string, unchanged. In this case, we have all the variables we need except for the length. The only unknown in this expression is the length of the string that should vibrate in order to produce the musical note C, and we can solve for that very simply to yield the result 0.544 meters, which is shorter than the string was originally, as expected.